I'll be doing a article review on AMPK activated kinase by Isorhamnetin and how it protects hepatocytes against oxidative stress and mitochondrial dysfunction. So I would like to give a introduction on AMPK, otherwise known as AMP activated protein kinase. It is a kinase that is a regulatory kinase for many catabolic pathways, including here we can see a pathway for glucose deprivation where it activates the influx of glucose using GLUT4. Here is a pathway where it inhibits fatty acid synthesis, and it also encourages beta oxidation so that it increases the ATP concentration within the cell. A key pathway in activating AMPK is through liver kinase B1. Here we can see pathways of how AMPK responds towards reactive oxygen species in moderate hypoxia, where it activates the reactive oxygen species activates the endoplasmic reticulum to activate calcium-mediated kinase, which would then activate AMPK, which will then regulate the mitochondrial activity so as to prevent hypoxia from being fatal. So the researchers are specifically interested in a pathway where phospholipid within the cell is transformed into arachidonic acid, and when catalyzed with iron can form reactive oxygen species within the cell, right? And how AMPK can regulate the mitochondria to prevent apoptosis within the cell. A key component of this is isorhamnetin, which the researchers are interested to see if it can activate AMP kinase and how it can be cytoprotective within the cell. So isorhamnetin is a cytoprotective compound which can see antibacterial, anti-inflammatory, antioxidative, and anti-hypoxic properties. If we look into the fluorescent microgram over here, we can see that it has a protective effect against Staphylococcus aureus infection. So one of the first figures within the graph is a flow cytometry graph where we can see that the cells were treated with arachidonic acid or isorhamnetin. And in the control, we can see a low amount of dead cells which were stained using propylium iodide, which stains for dead nuclear components. However, when treated with AA plus iron, we can see that a increase in the population by PI staining, showing that there is a increase in dead cells. However, this is resolved upon treatment with isorhamnetin, showing us that isorhamnetin has a protective effect on AA plus iron treatment. We also see from the Western blots that we have uncovered the pathway of cell death, which would be via apoptosis, as we can see a decrease in procaspase 3 as well as BCL-XL, indicative of the intrinsic pathway of apoptosis. Isorhamnetin has also been shown to decrease the amount of reactive oxygen species within the cell. We can see over here at graph A, when in the control setup where there's no treatment of isorhamnetin of AA plus iron, we see a basal level of reactive oxygen species. However, upon treatment with arachidonic acid and iron, we can see a stark increase in the amount of reactive oxygen species within the cell, and a mediation of that by isorhamnetin once again. The researchers also go on to measure glutathione, which is a antioxidant within the cell, and similarly we see a basal level with AA plus iron treatment with no treatment in the control. However, upon AA plus iron treatment, we see a stark decrease in the amount of antioxidant activity within the cell, but we see a maintenance of the antioxidant concentration within the cell by isorhamnetin treatment. The researchers then move on to hypothesize that the mitochondria is therefore the source of the activity, and therefore use bromidine stain, which is a direct correlation to the mitochondrial activity within the cells, and runs FACS to be able to quantify the mitochondrial activity. So within the control, we can see high fluorescence and high absorbance within the mitochondria, indicating that mitochondrial activity is high within the control setup. However, upon treatment with AA plus iron, we see a RN1 fraction which has low absorbance, right, and a decreased amount of fluorescence in the high activity, high absorbance spectrum for the Romatan dye. And again, it's resolved upon treatment with Isorhamnetin, indicative that AA plus iron treatment is responsible for decreased mitochondrial activity, and once again resolved by Isorhamnetin. So next, the researchers would like to validate AMPK as the downstream target of Isorhamnetin. So over here we can see Western blots showing that within without any treatment of Isorhamnetin, we see no activated AMP kinase. However, upon treatment with Isorhamnetin, we can see an increase in phosphorylated AMP kinase, and we can also see its downstream effector, ACC, to be phosphorylated. Therefore, we can conclude that AMP kinase activates ACC and is activated by Isorhamnetin treatment. The researchers then go on to use siRNAs, which are transcriptional inhibitors of calcium-mediated kinase 2 and liver kinase B1, which I had stated before in my introduction to be key regulatory kinases of AMP kinase. So we can see over here within the diagram that in the treatment of Isorhamnetin, upon that AMP kinase phosphorylated AMP kinase had been decreased whenever calcium-mediated kinase 2 is inhibited by siRNA, indicative that that CAMKK2 is the key regulator of AMP kinase by Isorhamnetin treatment. The data for LKB1 is however not shown, and is one of my main criticisms of the paper. There had been no supplementary data, or no graphs or figures, or simply a explanation given on LKB1, and therefore I believe that there could be some mishap in the data. The mitochondrial activity is also quantified. Is checked using compound C as a inhibitor to confirm that AMP kinase activates mitochondrial activity, or in this case inhibits mitochondrial activity as its pathway by Isorhamnetin activation. So we can see that the RN1 fraction, which I had introduced before as a low activity spectra, has been shown to be at high levels when the cells were treated with AA plus iron, and maintained despite compound C treatment, but lack of Isorhamnetin, indicative of a control setup. However, upon treatment with Isorhamnetin, we see a large decrease in the RN1 fragment, showing us that there had been high levels of mitochondrial activity, but when compound C is added, it decreased the amount of mitochondrial activity, indicative that compound C inhibits AMPK, which had been activated by Isorhamnetin, and therefore decreasing mitochondrial activity, leaving Isorhamnetin activated AMP kinase as the clear pathway of Isorhamnetin. So I would like to give a brief discussion on the researchers' conclusions as well as the data. So first off, we had established that AA plus iron treatment causes an increase in reactive oxygen species, and that Isorhamnetin decreases the reactive oxygen species within the cell, as well as maintains the antioxidant glutathione within the cell. And we had also confirmed that the mitochondrial activity had been the main factor affecting the cellular activity using the Romatan dye staining. And therefore the researchers attribute the mitochondria as the probable source of reactive oxygen species production. However, AMP kinase had therefore had a protective effect against the mitochondrial dysfunction. However, I disagree with the researchers, and I think that the data is contradictory to some of the data that we had seen earlier. given that we had seen a decrease in procaspase 3 and BCL-XL in AA plus iron treated cells, right? As we can see here, the reactive oxygen species activates pro-apoptotic element BAX, which is inhibited by BCL-XL, and therefore a decrease in BCL-XL would be indicative of apoptosis, right? As well as a decrease in procaspase 3 upon AA plus iron treatment would be indicative of procaspase 3 activation into caspase 3, and therefore the activation of the intrinsic pathway of apoptosis. The glutathione data had also been shown what I believe to be insignificant due to the fact that the total cellular glutathione within the cell is only minor in the mitochondria, and therefore I believe and I hypothesize that arachidonic acid, when catalyzed by iron, activates a different pathway which increases the reactive oxygen species within the cell rather than the mitochondrial dysfunction hypothesis that the researchers propose. However, it is also important to respect the alternative hypothesis where arachidonic acid in iron does cause mitochondrial dysfunction, creating reactive oxygen species, which then goes on ahead to reactivate BAX, and therefore causing the intrinsic pathway of apoptosis, and therefore leading to a data set that would be similar to what we see with the researchers. However, I still disagree that on the hypothesis of mitochondrial dysfunction. However, with my hypothesis, we can understand with the data that isorhamnetin indeed activates AMP kinase, but we are unsure on the pathway of which AMP kinase and how it activates or regulates reactive oxygen species within the cell, and how it regulates apoptosis within the cell. However, it had been shown clearly in the data, the first data within flow cytometry, that apoptosis is inhibited by isorhamnetin treatment. So, any questions, please?
Okay, thank you very much, Julia. That was very, very good, very clear, and just about perfect for time as well. Maybe the slide where the evidence they provided that the activation of AMPK was working through calcium and CAMKK, that was based on siRNA, was that right? Could we go back to that slide?
Yes, no problem. Just give me a second here. Are you seeing the slide change?
No. Incidentally, are you using? Did you share the application rather than sharing the?
Yes,
oh,
I
yeah,
shared
it's
the
changing
application.
now.
Right, it's all right. We're over here now.
Oh yeah, the siRNA. So they and it's in part C. They knocked down. You mentioned that they didn't show any data for LKP1 knockdown, which I agree these days you should do in supplementary data. But the knockdown of CAMKK2 seems to be very. The amount of knockdown they've got is very trivial, isn't it?
Yes. In fact, this is another criticism I have, which I did not have time to talk about within the paper. Right. It is quite clear that they wanted to show that that a decrease in CAMKK activated AMP kinase when treated with the siRNA. However, we can see that when in the control setup, whether there's isorhamnetin treatment or not, there is really no change in phosphorylated AMP kinase. Therefore, the decrease really doesn't really make much of any sense. In fact, when you compare it with the control setup where there is no isorhamnetin treatment, the siRNA is already significant enough to really knock down AMP kinase. So, like and of course, as you stated, right, the increase over the knockdown amount of CAMKK2 within the bands, we can see is quite insignificant as well. So therefore, it's quite curious what really is going on over here, especially curious that they did not provide supplementary data or even just a graph or a description of how LKB1 and what its data looks like.
Yeah, I agree with you. I mean, we've these days we would tend to use CRISPR for doing knockouts rather than knockdowns, rather than siRNA. But we have done siRNA in the past with CAMKK2, and the knockdown we got was much better than they have. So the conclusion from that figure, in my view, is that the siRNA is not working very well, actually. Anyway, okay, we'd better move on. Thank you very much.
All right, thank you.
So if you could stop sharing.